All right, welcome back, and now we're going to introduce Theorem 2, which is the differentiation or the derivative of the natural log function. Okay, so it says if x is greater than 0, right? Why does x have to be greater than 0? Because the domain of log functions are the positive reals. Okay, so if x is greater than 0 and y equals the natural log of x, then the derivative of y with respect to x is equal to 1 over x. Okay, so that's the specific case, right? Natural log of the derivative of y, the derivative of natural log of x is 1 over x. Okay. Now, more generally, if we have some general function g of x as the argument, so instead of x, we replace it with g of x. Okay, it says more generally, let g of x be a differentiable function for all values of x for which g prime of x is greater than 0. The derivative of h of x equal to the natural log of g of x now. So now we're going to put a more general function of x in here. That the derivative of this function is given by this. H prime of x is equal to 1 over the function. So up right here, see here the function is just x. So it's 1 over x times the derivative of the function, which is in this case x. The derivative of x is just 1. So we just multiply 1. So the general case also works for this specific example here. So in general though, if we're taking the natural log of some function, it's 1 over the function times the derivative of the argument, the function, right? So the derivative of h of x equal to natural log of g of x is going to be 1 over the argument, which is g of x, times the derivative of the function in the argument, which is g prime of x. So what's the proof? Let's do the proof. Okay, so let x, of course, we start with your assumptions, right? We're going to let x be greater than 0 and y equal, in this case, natural log of x. Okay? So let's do that. So, assume x is greater than 0 and y equals natural log of x. Okay. Oops. Okay. And since y equals the natural log of x, we know x equals e to the y. Now if we differentiate both sides of this, so what do we get? We get what? Well, on this side here, we just get 1 equals, on this side here, what do we get? Well, it's an exponential, So what do? We rewrite the exponential e to the y times the derivative of the exponent, which in this case is y, so the derivative of y is just dy dx. So we're doing implicit differentiation here. And then we solve for dy dx. So dy dx equals 1 over e to the y. And then we substitute back for what we said here. X equals e to the y. So we substitute back, which equals 1 over x. Now, we may also derive this result by applying the inverse function theorem as follows. Okay, so we could do it this way. Okay? Since y equals g of x equals natural log of x is the inverse of f of x equal to e to the x, e to the x, by applying the inverse function theorem, what do we get? Well, here, since y is equal to g of x equals this, is the inverse of this, what we can use is we can get dy dx we have, and we dy dx equals one over f prime of x I'm sorry, not g of x. Okay. Now, look, here, all we're using is the fact that for this exponential e to the x, the derivative of e to the x is just e to the x. Okay, so when we do this composition here, f prime of g of x, all we're going to get is 1 over, well, it's just going to be e to the g of x, which is the natural log of x, and then of course this is a natural logarithm, this is the natural exponential. They both have the same base, so the inverse terms, they're going to cancel each other out, and we end up with the same result of 1 over x. Because remember, when you compose an inverse function, when you compose two functions that are inverses of each other, you always get x out. Now, using this result and applying the chain rule, this is what we get. So h of x I should write that down. So using this result, and applying the chain rule, we have, let's see, okay, 2 h of x equal to natural log of g of x we obtain what? H prime of x is equal to 1 over g of x times g prime of x. And that's it. So we obtain the same thing. Okay, so now what we're going to do is we're going to look at some examples of this and applying these to logarithms. So basically, what do I want to say here? We're going to look at some examples and show how we're going to apply these different problems involving logarithmic functions. Okay, and again, we can combine these with other rules as well, given the fact that we can use the different differentiation rules. Okay, that's it. Have a great day.